Okay, so first of all, I'm not going to be showing the code here very much. I'm just going to point out that all we're using to do this is NumPy. All we're doing to use this is NumPy. I want you to understand this, what this actually means. And here it is a little bit of an explanation that what is an FSP and why does it matter. So an FSP is a fractional scale process. I call them fractal sigmoid processors too. So that works as an acronym, and you'll see that at the end. But what it is, it's a cutting-edge mathematical framework, and it's designed to model systems that evolve over many scales of time and space. So there's many of these processors running at the same time. It's a multiprocessor system, temporal processors. And it works by combining two key ideas. So first, there are deterministic past kernels. These remember the history in a reliable deterministic way. And we'll find more about that as we go through here. Then there are probabilistic future kernels. So there's deterministic past, probabilistic future. That makes sense, right? The future dynamics are governed by probabilistic rules capturing uncertainty. So this blend allows these fractal scale processors to realistically simulate complex real-world phenomena where present depends on a mix of well-remembered history and uncertain future possibilities. The present depends on a mix of well-remembered history and uncertain future possibilities. So that's our experience of temporal flow, basically. So again, we set up with we're just going to do some plotting here, but basically this is all running on NumPy. And there is, down here, step 1, this basic single scale dynamics without memory, or without folding and without unfolding. This will become clear what that means down below, but this is a simple cell. What happens here, we just set up and run a simple version of the model. It simulates how a small set of key variables change over time in a controlled random environment. So it's a simulation, it's a time simulation. And the model includes a smooth gating mechanism that modulates how these variables evolve on a clock that influences their dynamics, and the goal is to observe the basic behavior without employing any memory or without employing any complex interactions to ensure that the system is stable and is behaving as expected before we take the next step. And so let me pause the video for a second and go past the code. Alright, so here are the two systems, the two states. There's mode 1, which is the heavily grained one, and there's the mode 2, which is the fine grained one. So these are two interacting systems. They have their own separate behavior, but they are interdependent on each other. So what we're going to do now is we're going to add fractional memory convolution, and this will become clear. Let me remove this top part here. So what happens in this cell? In this step, the model is enhanced to remember its past behavior in a sophisticated way, instead of just reaching out to the current state. The model now includes a fractional memory component, meaning that it blends recent and older past states with gradually decreasing influence over time. What that means is what just happened a second ago is more important to me right now than what happened 2 seconds ago, which is more important than what happened 3 seconds ago, like that. So it's a decremental perspective on a fading past. Okay. So then it has decreasing influence over time. This memory effect is incorporated through a special kind of weighted average called a fractional convolution of all past states. It allows the system's current state to depend not only on the present but also on the history. So the rest of the system's dynamics, the gating, the noise, the clock, they continue just like before, but now it's influenced by its memory. Now right now you're going to say, well, if it's trailing into the past, how does it remember its history? Because it's going to fade more and more, and it's just going to remember the near history. It's not going to have a long memory. Well, there is an answer for that. We'll get to that down below. But why is this important? Because it captures real-world memory effects. Many real systems don't just react to what's happening right now. but are influenced by their entire history. For example, markets, biological systems, climate models, these all show long-range dependence that simple models just miss. So what we're doing here now is improving the model's realism by adding this fractional memory. The dynamics become more realistic, more robust, and they better reflect the complex behaviors where past states matter. And then it gives also a foundation for complexity, because this memory aspect is key to the power of the full fractional scale process model, enabling multi-scale memory effects and nuanced system evolution. So it's contributing a memory effect. So how does this contribute to the project's goal? It moves the model from a memoryless system to one that effectively captures gradual forgetting and last influence of the past. It improves it provides a stepping stone towards building a multi-scale adaptive model that understands both the depth of history and immediate changes at the same time. So what this does is it makes the model much more flexible, much more powerful for simulating complex phenomena important in business and science. And I will say that right now we have two models. We have two models going on. We could have 5 or 10 models. It's not just one fractal processor that can converge in an influence field. It converges their fields of influence. It could be many more than just 2. This is just my first crack at it, so I'm just putting 2 together. It's a brand new concept, that emerged out of the math last night. In brief, this step brings in a mathematically advanced but computationally efficient way to remember the past when predicting the future, making the system smarter and more capable of capturing the nuances of real-world dynamics. So let me pause the video again so I can get past the code. It's a little bit secret. Okay, so now that the system can remember, then we can see more of a correlation between their trajectories, their temporal trajectories. So they have aligned themselves over time now that we've put the memory here. You see how much better that is? This is important right here, because what inspired me to do this is because I was working on that stock trader. So just let me compare the difference between this up here. You see that? From a stock trading standpoint, think what this might mean if we go and look now down at the bottom at this down here, right? So this is important. It works for a lot of things too, not just one thing. All right, well, what about step 3? And now here comes a very interesting fact. This is the dragon eating its own tail, or the DEOT, if you want to use an acronym. This is what just hit me last night. That we're going to introduce this fold-unfold operator. It's a single scale fold only. So what happens in this cell? This step adds a novel ability to the model. It can be compressed. It can fold complex high-dimensional information into simpler summary, and then reconstruct or unfold the information back to its original form almost perfectly. You'll see what I mean by almost down below. We have some measurements of this happening. Now what the fold operator does is it takes the detailed current state and produces a compressed representation of it. It's like summarizing a large document into just its key points. Then the unfolder operator, it takes that summary and it rebuilds the detailed state, and it recreates the document from those key points. This is huge, actually, right here. It's an innovation beyond what I can describe in a short video. But anyway, after performing the fold and unfold operations in sequence, the model then checks the original detailed information, makes sure it's closely recovered, and then it ensures that folding and unfolding is reliable. So this is complexity reduction, right? This is R truncation on steroids, and it can happen simply on my CPU because it was a very important mathematical discovery that I made late last night, by the way. Okay, so after performing the fold and unfold operations in sequence, did I already read that? Yeah. The simulation also continues to incorporate the fractal memory, and the dynamic gating is just like before, but now it's combined with these folding and unfolding steps so that we can do we can do comprehensive synthesis more easily and without the high computational load. So why is this important? Data compression and efficiency. Folding, it reduces the complexity. It makes it easier to process. It makes it easier to analyze large-scale systems without losing the essential details. So multi-scale modeling foundation. It's a foundation for multi-scale modeling, not just one scale, remember. This fold-unfold mechanism is critical for managing information across multiple scales in the full FSP framework, capturing key system features at different levels of detail. So it also contributes to model stability and consistency. It verifying that the folding followed by unfolding returns nearly the original state. It assures the model maintains accuracy when compressing and expanding information, which is critical for trustworthy predictions. And so then we're going to look at the graph of that down below. So how does this contribute to the project's goal? Well, it equips the model with tools to summarize and restore system states efficiently. So it can summarize and restore efficiently, enabling the handling of complex spatial data without overwhelming computational resources. This is a key innovation. It's key. This will drop data, like a data center's overhead. It will drop it like a lot, okay? This alone will this algorithm will alone change everything. So this capability is vital as we build towards multi-scale dynamics where information flows between coarse and fine resolutions. So you're going to have 10 of these competing dynamics in one complex system. They're loosely conjoined, they have memory, they have prediction, and they're influencing each other, okay? And that's not easy to do. I mean, the computation there has traditionally been, untenable, but now we have a solution. We have a solution. So what this does is it ensures that the model can scale up while keeping simulations stable, accurate, and computationally feasible, advancing towards a powerful and practical fractional scale process. So in brief, step 3 adds a smart fold and unfold compression mechanism, like summarizing and reconstructing information. And it maintains the accuracy, and it improves the efficiency, and it lays an essential groundwork for modeling systems across scales while keeping computational demands manageable. So I'm going to pause the video to get past the code here. Okay, so these are approximations, so they're averages, but we've got the folded mode 1 and folded mode 2. This is the truncated version, the low intensity version, the summary version, and this is the expanded version, and they do fold and unfold. Yep. They're not perfectly conjoined. You see there's a little bit difference, but that's expected because what we did when we folded is that we lost information, and so when we unfold we expect some variance, but this is within tolerance that we can it's faithfully representing it, so we can get a good summary and go back out to the original full form of the system. They used to have to use GAPI partial differential equations for this, highly complex, to summarize the system so you can run control signal, so you can analyze it and run a control signal back. You run that control signal back to the system, then it changes the system. So you have to expand back to the expanded complex view, take another snapshot to compress that again using fast computation, doing that all in real time? No. This used to be very hard. We have a massive solution right here. This is very, very important. So the folding and unfolding actually works. And this arose out of a synthesis of really powerful mathematics, which I'm not going to show you right now. Okay, so here's the step 4. You add a second scale without coupling. So we're going to add that second scale now. So what happens in this cell? Well, in this step, the model is expanded to include a second level of detail, or a second scale, alongside the original one. So imagine having both. So a coarse view, scale 0. So remember, the coarse view is going to be scale 0. And then that captures broad overall patterns. Then you have a finer view, scale 1, which captures more detail, smaller scale behavior. And this is important because in the macro world, you still have quantum flux that influences things. You still have probabilities everywhere. So the coarse view is the deterministic view. It can be. And the finer view can be the probabilistic view. That also can be. And you'll see that coming, that we're adding future here is what we're doing. We can already deterministically look at the decrementally weighted past and keep a history, but we're going to also be adding a more probabilistic container here. So each scale has its own internal state, its own time clock, and it evolves independently, and they don't really influence each other at this stage. So both scales undergo their own separate dynamical changes, their own memory effects, their own noise, and their own gating mechanisms. They're not joined. Effectively, the model runs two separate simulations side by side right now, one at low resolution and one at higher resolution, but without yet linking these scales. So the coarse one is low resolution, 0, right? 0 is low res, and the scale 1 is high res. And they're running conjoined. They're running concurrently, but not conjoined, right? So why is this important? Multi-scale representation. Many complex systems, they operate simultaneously at different scales, like weather patterns over continents or local winds in a city. Then this system can capture multiple scales, and this is often critical for realistic modeling. So there's also model modulation here. So by first implementing the independent scales, the model is made modular. It's easier to understand, it's easier to test, and it's easier to later integrate. The foundations for coupling. So establishing independent scales is a necessary stepping stone before introducing interactions between scales, which will add richness and realism to the model. So how does this contribute to the project? Well, it begins the transition from a single scale model to a more powerful multi-scale framework, a key to the fractional scale process. So now you can have really, really complex processing happening together because they're fractal. They know it, they're conjoined, but you're not going to have latency. So you've increased the speed dramatically by the folding and unfolding, and then you've been able to put together multiple coordinated processings very, very easily here with this system. This enables the future coupling of scales where dynamics at one scale can influence and be influenced by other scales, other dynamics. So this increases the expressiveness and the fidelity of the model to handle complex real-world systems that have behaviors that evolve simultaneously at different levels of detail. So in brief, step 4 adds a second layer or a second scale of the system operating alongside the original one, each evolving on its own. This sets up the groundwork for a multi-scale modeling, essential for capturing complex phenomena over different levels of detail. A core goal of this project. All right, let me pause the video and I'll show you the graph of that down below. Okay, so here you have the coarse one, and here you have the fine one, and they're independent still right now. So now what we want to do is this is complicated, so you might not catch this the first time around. It involves the tricky math that's going on. So the fold and unfold between scales without coupling. So at this step, the model adds an important capability to connect these two scales that we've implemented earlier, scale 0 coarse and scale 1 fine. So the fold operator, there's an equation here, it compresses the detailed fine-scaled information. It compresses C1 into a summarized representation that fits the coarser scale, C0. Think of extracting the key summary trends from detailed data. So then the unfold operator, it then does the reverse. It takes the coarse scale information, C1, and expands it back into a detailed fine scale approximation. So this is like recreating finer details from a higher level summary. So we're taking the high level one and we're compressing it. We're taking the low level one and we're expanding it in a way that we can match them together, you see. So in the cell, these two operators are implemented and tested independently in this cell, but down below, cell 5. I won't show you the code here, but What we're doing is seeing if this works, right? We're testing them independently without the scales interacting dynamically yet. No coupling yet. We're just scaling them independently. The test involves checking if folding the fine scale produces a valid coarse scale summary, and then if unfolding that summary reconstructs the fine scale features meaningfully. Adding folding after unfolding. Additionally, folding after unfolding is checked to be approximately consistent, meaning that the fold and the unfold should closely resemble the original fold. So you're going to fold, you're going to unfold. So you have the original. Anyway, it's complex, like I told you. So why is it important? So bridging scales. This establishes a translation mechanism that moves information up and down between fine and coarse levels, essential for multi-scale modeling. The consistent representations. So this ensures that the model can compress and expand information between scales without losing any critical detail or any inconsistencies. So the foundation for coupling dynamics. So it gives us a foundation. This step prepares the framework for the next stage, which you'll see below, where the two scales will actually influence each other through their folding and unfolding representations. So how does this contribute to the project goal? It enables information flow between scales, a hallmark of fractional scale processes that model complex systems with interacting structures and multiple resolutions. Then it also facilitates efficient computation, since operating at the coarse scale is faster and can summarize the fine details, while unfolding can reconstruct the details whenever we need to. And this lays the groundwork for more realistic and powerful models, capable of capturing dependencies across scales, improving prediction and understanding of the complex dynamics. So step 5, it builds the crucial communication channel between details and summarized views of the system by folding fine scale data to coarse scale summaries and unfolding coarse scale data back to fine scale. This capability is essential for creating accurate multi-scale models that efficiently capture complex system behaviors. So this is the really hairy math. Nobody's going to crack this. This is actually one of our IP protections, that this mathematics is avant-garde, right? It's next level, and nobody's going to crack it. So let me show you the visualization down below. Hold on. Okay, so this is the folded and this is the unfolded. So here's the compressed. You see the values here, and here's the expanded. And yes, in the summarized one, you would expect you have less information here already. So when you summarize, you expect to get a smaller summarization than you get when you compress something larger. So it's like this is the master and this is the slave because of their size differential. But we take the original one, we fold it, we get this, and then we unfold it and we get back to what it should have been, what it was before, the original state. Fascinating. Okay, number 6. We're almost done. Bear with me. So weak coupling between the scales in dynamics. This is important. Again, there are realizations here that nobody else has, so we're safe, right? Our IP is safe because of the comprehensional strength of this. What happens in this cell? In this step, the model takes a big leap from treating two scales independently to allowing them to interact, but only gently. So this is weak coupling. There's a reason for that, which will become apparent. The fine scale system, scale 1 dynamics, now gets a subtle influence based on the current state of the coarse scale system, a subtle influence. Specifically, a summary of the coarse scale's state, its folded representation. So this is added as a small driving force to the fine scale's evolution. Both scales continue to have their own memory, their own noise, their own gating dynamics, but now with this cross-scale feedback, they're no longer isolated from each other. This is key. The two independent clocks and the two independent states, they still persist, but the fine scale's change partly depends on the coarse scale's recent behavior. So this simulation here runs to show how the two scales evolve together with this weak interaction added. So why is this important? Because it captures realistic interactions. Many complex systems have processes operating at multi-levels influencing each other. So, for example, regional climate impacts local weather. organizational strategy influences team dynamics. Modeling these cross-scale interactions is key for realistic behavior. So it also is important because it's a transition toward integrated multi-scale models. So it's never been possible before. In the real world, you could do it. You could do it with massive computers and in some forensic laboratory, but now we can do it out on the farm, out in the dirt. So we're moving from independent scales to coupled scales. This enhances the model's ability to represent dependencies and feedback loops across different scales. It maintains stability. So by starting with weak coupling, the model controls complexity and helps avoid instabilities, making it easier to understand and tune. But remember, it can always go back to the original state with a flip of the switch to make sure it gets stabilized. It doesn't diverge. So what I mean is that over time, you'd expect the fine and the coarse representations to begin diverging, but they're coupled, so they don't. So they can always look back at the original unfolding, the full unfolded version. In fact, they do. So how does this contribute to the project's goal? It introduces multi-scale coupling, a fundamental feature of fractional scale processes. It enables scales to dynamically influence one another. And this crosstalk between scales, it boosts the model's expressiveness and its predictive power, allowing it to capture richer system behavior that single and uncoupled scales cannot. And it provides a basis for future refinements. It's like, for example, stronger coupling, adaptive interactions, or learning cross-scale dependencies from data, which again, you're going to see a little bit of that, what that means down below. But in brief, step 6 connects the previously independent coarse and fine scale dynamics by adding a controlled weak influence from the coarse scale onto the fine scale. This coupling reflects how multi-scale systems in the real world, how they interact, making the model more powerful and realistic as a tool for understanding complex multi-layer dynamics. All right, so let me pause this and show you the graph. Okay, so here are the coupled dynamics. So you have the mode 1 and mode 2 scale down here. You have mode 0, mode 1, and then you have scale 1 and scale 2, and then you have scale 1, mode 2, scale 1, mode 1, and then you have scale 1, mode 2, which I'm not going to get into right now. But suffice it to say that this is exactly what it should be doing. They should know each other. They should track together. Okay, so then finally the adaptive kernel dynamics. So what happens in this cell? This is interesting. At this stage, the model improves the way it processes information across scales, across space, by making the folding kernel essentially a spatial weighting function. It makes it adaptive rather than fixed. This is important because I think if you think about consciousness, we have states where we're sleeping, and we may have more. We don't care about the future. Or we may be contemplative, where we're just really thinking about the past. So our energy, the energy of our thoughts, of our focus, the energy and focus is moving, towards the past. And sometimes we're really focusing on a problem where, but it's an intellectual problem. So we've totally forgot about the past, and we're just, we don't know where we are in time or space because we're in a mental place. That would move all of your energy towards the future, right? And all your focus and energy towards the future. But then there might be a lion that suddenly starts attacking you, where you spread a very intense amount of energy to the past and the future. All the energy is really focused around, in more of a symmetrical way. So we can do this now because it's the weighting function of past and future kernels is adaptive now. I don't know if that makes sense. But anyway, initially the kernel weighted 1 is a fixed pattern, and it determines how the system summarizes or how it folds the fine scale information. But now the kernel updates itself continually based on the energy or the intensity of the current fine scale state. If the certain spatial regions have a higher energy or more activity, the kernel adjusts to emphasize or to weight those areas more. So this adaptation happens gradually. using a feedback rule that nudges the kernel towards the matching energy pattern. So the kernel values are kept within sensible bounds to maintain stability, and so it does adapt gradually. It doesn't just jump, right, because that would destabilize the system. But over time, this adaptive kernel better reflects the actual spatial patterns in the dynamic system, improving how fine details influence course summaries. So you know how models get trained in the statistical world? Well, this is a learning system, temporally learning by experience. This is interesting. This is very interesting. Why is this important? Because dynamic spatial sensitivity. Instead of a static, one-size-fits-all spatial focus, the kernel pivots to what's dynamically important in the system, enhancing its responsiveness. Secondly, it has improved representations. By adding to the system's current energetic landscapes, the summarizations or folding more accurately highlight critical spatial features. It adapts to the system's current energies, so it becomes more accurate. Okay, it's also biologically inspired because it mirrors how real-world complex systems like the brain or like climate systems can adapt their internal focus or weighting based on the changing activity patterns. And this is a foundation also for synthetic learning because adaptive kernels enable the model to learn spatial patterns autonomously rather than rely on present assumptions. So it has a memory, and it can move the intensity of its memory more towards the past. So it can have a long-term or short-term or mid-term representation based on the focus and the energy modulations that are asymmetrical to past and future, right? Like past categorization and future prediction. It can change its focus and its energy force in this domains. How does this contribute to the project's goal? Well, it enhances the accuracy and flexibility of the multi-scale modeling by letting spatial weights evolve with the system's state. It boosts the model's ability to capture complex spatial temporal interactions by dynamically tuning how information is integrated across space. It moves the model closer to real-world complex systems where connection strengths and influence zones adapt over time. And this sets the groundwork to incorporate more advanced learning or optimal techniques for even more powerful predictive models. So in brief, step 7 enables the model to adjust how it spatially weights the fine-scale data by evolving an internal kernel based on current activity levels. And this dynamic adjustment, it makes the model more realistic, more responsive, and more effective in capturing complex spatial patterns in multi-scale systems. And this is a key step towards building this adaptive, intelligent models of complex dynamics. So I'm going to pause the video and show you the visualization down below. So there it is. That is the negentropic nexus. This is the focal point of the present consciousness as it flows through time. It's smart. This is a picture of an AGI.